Look up at the night sky on a clear evening, and what do you see? A scattering of quiet, steady points of light, a serene and almost peaceful canvas. It's a beautiful illusion, a cosmic magic trick that hides the breathtaking truth. The universe is not a still and silent place. It is a riotous, chaotic, and utterly bizarre arena where the rules of reality as we know them are being rewritten every single second. What if I told you that the cosmos is a stage for events so profoundly strange, they actively defy our very understanding of physics? That right now, as you watch this, stars are being drained of their life force by invisible companions. Colossal explosions are tearing through the fabric of space-time, and structures so vast they seem like impossible, invisible walls are shaping the entire architecture of existence. This isn't the plot of a science fiction novel. This is the genuine, jaw-dropping reality of our universe, and we are living right in the middle of it. The tranquility of the night sky is a grand deception, masking a celestial drama of epic proportions playing out all around us. This video is your front row ticket to that spectacle. We are about to embark on a journey, a countdown through 25 of the most mind-bending, head-scratching, and awe-inspiring phenomena currently unfolding across the cosmos. We will venture beyond the placid stars to encounter stellar vampires, dying stars that cling to their larger neighbors, siphoning away their energy in a desperate, eternal dance. We will witness the ghostly signatures of dark matter, a substance so enigmatic that it makes up most of the universe's mass, yet remains completely invisible to our eyes and our finest instruments. We will explore the possibility of cosmic cracks and defects, relics from the universe's violent birth that may have created flaws in the vacuum of space itself, barriers that could truly be described as invisible walls. Each entry on our list is a testament to just how wild, how unpredictable, and how utterly magnificent our universe truly is. This exploration is about more than just cataloging weird facts. It's about tapping into a fundamental human drive, our insatiable curiosity. For all of human history, we have looked up and wondered, and today we have the incredible privilege of beginning to find some of the answers, only to discover that those answers lead to questions far stranger than we ever imagined. So get comfortable, open your mind, and let go of what you think you know. Together, we are going to pull back the curtain on the greatest show there is, revealing the bizarre, the beautiful, and the breathtaking events happening in the cosmos right now. Kicking off our journey into the cosmic unknown, we begin with a celestial projectile, a star on the run. In the constellation Ophiuchi, a colossal blue giant known as Zeta Ophiuchi is engaged in a desperate flight, hurtling through space at an almost unimaginable speed of 170,000 kilometers per hour. To put that staggering velocity into perspective, it's moving fast enough to travel from the Earth to the Moon in just a single hour. This isn't a leisurely cruise, it's a violent, chaotic expulsion. But how does a star, an object with millions of times the mass of our entire planet, get kicked out of its home? The most compelling theory points to a cosmic cataclysm of the highest order. Astronomers believe Zeta Ophiuchi was once one half of a binary system, gravitationally bound to an even more massive partner. That partner, living a short and furious life, would have reached its end in a supernova explosion of unimaginable power. In a binary system, such a detonation doesn't just destroy one star, it acts like a cosmic slingshot. The sudden, violent loss of mass from the exploding star would have instantaneously severed the gravitational bonds holding the pair together, literally flinging Zeta Ophiuchi away like a stone from a sling, sending it careening across the galaxy. And its journey is anything but quiet. As this stellar fugitive tears through the galaxy, it isn't moving through a perfect vacuum. It's plowing through dense clouds of interstellar gas and dust. The effect is spectacularly violent. Think of a speedboat racing across a lake, pushing a wave of water ahead of its bow. now scale that up to a stellar level. Zeta Ophiuchi's powerful stellar wind, a constant stream of charged particles flowing from its surface, slams into this ambient material. This collision compresses and heats the gas, forging a gigantic, glowing wave that wraps around the star in a parabolic shield. This is a bow shock, and it glows most brightly in the infrared part of the spectrum, a fiery testament to the star's incredible speed. Visualize this: a brilliant blue-white star, searingly hot and luminous, is seen plowing through a delicate, wispy cloud of cosmic dust. Ahead of it, the material is not just being pushed aside, it's being superheated, sculpted into a brilliant, curved wall of light that looks almost like a flame wrapping around a spaceship entering an atmosphere. This is not a gentle process, it's a continuous, high-energy collision, a visible scar that the runaway star leaves in its wake, marking its path across the heavens for all to see. Moving from a star flung across the galaxy, we find an equally astonishing object much closer to its home, a world of almost mythical luxury and unimaginable heat. Imagine a planet where the ground beneath your feet, if you could stand on it, might be composed of glittering diamond. This isn't a fantasy. It's the best explanation for the bizarre reality of 55 Cancri e, a super-Earth orbiting a sun-like star just 40 light-years away. The most staggering thing about this world isn't just its proposed composition, but its frantic pace of life. It races around its parent star at a blistering speed, completing an entire year in just 18 hours. To put that into a human perspective, you would celebrate your next birthday before you've even finished a single day on Earth. This incredibly tight orbit is the key to its hellish nature, locking the planet in a gravitational embrace so intense that it creates conditions far beyond anything we know. This close proximity results in surface temperatures that are almost incomprehensible, soaring to around 2,700 degrees Celsius. That's hot enough to not just melt rock, but to turn entire landscapes into a global, roiling ocean of molten lava. Scientists hypothesize that one side of the planet is permanently facing its star, caught in a tidal lock that creates a hemisphere of perpetual, scorching daylight, while the far side might theoretically be slightly cooler, though still unimaginably hostile. The sheer heat and radiation blasting the planet's surface would vaporize any known material, making it a cauldron of vaporized rock and mineral. But the true strangeness of 55 Cancri e lies beneath this incandescent surface. The prevailing theory, based on its density and the composition of its star, suggests this is a carbon-rich world. Unlike Earth, which is oxygen-rich and built from silicates and iron, this planet is likely dominated by carbon and its compounds. Under the immense pressures found within a super-Earth, that carbon is compressed into its most stable, crystalline forms, graphite, and incredibly, diamond. It's possible that a significant portion of the planet's interior is a solid mass of diamond, a literal treasure trove on a cosmic scale, buried under a global ocean of fire. The existence of such a world throws a massive wrench into our standard models of how planetary systems form. Astronomers once thought that all rocky planets would be chemically similar to the inner planets of our own solar system, built from the same oxygen, magnesium, and silicon-rich debris circling a young star. 55 Cancri e shatters that assumption. Its discovery implies that some stellar nurseries can be incredibly rich in carbon, giving rise to a completely different class of worlds. Instead of a mantle of rock like Earth's, this planet could have a mantle of diamond with a core that might be solid carbon as well. It forces us to broaden our imagination and accept that the universe has a much richer palette for planet building than we ever anticipated. This glittering inferno stands as a stark reminder that the cosmos is capable of creating wonders that defy our simplest expectations, forging worlds of immense value in environments of equally immense destruction. Our journey now takes us far beyond runaway stars and diamond worlds to a scale so vast it encompasses entire galaxies. But even here, among these colossal islands of stars, we find a story not of serene isolation, but of cosmic consumption. Our next bizarre event involves our closest large galactic neighbor, the magnificent Andromeda Galaxy. To the unaided eye, it's a faint, ethereal smudge in the night sky, a seemingly peaceful spiral. The reality, however, is that Andromeda is a gravitational predator, a cannibal currently in the process of devouring its smaller galactic companions. This isn't a future threat or a past relic, it's an ongoing celestial feast, and the evidence is scattered all around it for our telescopes to see. When a large galaxy like Andromeda encounters a much smaller dwarf galaxy, the encounter is brutally one-sided. The immense gravitational pull of the larger galaxy doesn't just attract the smaller one, it begins to tear it apart. Stars, gas, and dark matter are ripped from the dwarf galaxy, stretched into long, flowing rivers of starlight that wrap around the predator. These are called stellar streams, and they are the ghostly remains of these cosmic meals. With powerful observatories, astronomers have mapped these faint, arcing trails of stars in the halo of the Andromeda Galaxy. They are the galactic equivalent of crumbs left on a plate, telling a clear story of multiple mergers and absorptions over billions of years. Some of these streams are still connected to their original, now severely damaged dwarf galaxies, like a comet's tail of doomed stars. Others are more diffuse, their stars already fully assimilated into Andromeda's outer reaches, their origins slowly fading into history. This process of galactic cannibalism is how large galaxies grow. They don't just form in isolation, they build themselves up over cosmic time by consuming smaller neighbors, growing fatter and more massive with every merger. And this brings us to the most profound implication of Andromeda's voracious appetite, a future event that directly involves our own home. The same gravitational dominance that allows Andromeda to tear apart dwarf galaxies is also drawing it inexorably toward the Milky Way. The two largest galaxies in our local group are on a collision course. In approximately 4.5 billion years, the Milky Way and Andromeda will begin a slow, majestic, and ultimately transformative dance. This won't be a violent, star-smashing catastrophe, as the vast distances between stars mean direct collisions are incredibly rare. Instead, it will be a gravitational upheaval. Over billions of years, the two spiral structures will be completely shredded and twisted by tidal forces, their orderly arms becoming tangled streams of stars. They will pass through each other, swing apart, and then fall back together, finally merging to form a new, larger galaxy, often referred to by astronomers as Milkomda. This future collision foreshadows a complete transformation of our night sky. As the merger progresses, the Andromeda Galaxy, which currently appears as a small fuzzy patch, will grow larger and larger, eventually filling a huge portion of the heavens. The familiar band of the Milky Way will be warped and distorted beyond recognition. Within this new, elliptical galaxy, the solar system will likely be flung into a much wider orbit far from the galactic core. While the planets will probably remain unscathed, the celestial scenery from Earth, should any life remain to witness it, will be utterly alien. The tranquil spiral we see today is a temporary state. The ongoing cannibalism we observe in Andromeda is a stark preview of the dynamic and often violent processes that shape galactic evolution, reminding us that even the grandest structures in the universe are not permanent, but are constantly evolving, merging, and being remade. From the chaotic galactic collisions shaping our cosmic future, we now turn our attention to a place of profound and eerie stillness. Out in the vast expanse, roughly 5,000 light-years from Earth, lies an object with a chilling distinction. It is officially the coldest known natural place in the entire universe. This is the Boomerang Nebula, a pre-planetary nebula where the temperature has been measured at a mere 1 degree Kelvin above absolute zero. That is a staggering -272 degrees Celsius, a depth of cold that is difficult for the human mind to even grasp. It is colder than the deepest, darkest voids of empty space, and incredibly, it is even colder than the ubiquitous background glow left over from the Big Bang itself. This isn't just a cold spot, it is the ultimate deep freeze, a monument to cosmic refrigeration. So, how does a place become this cold? The secret lies in the dramatic death throes of a central, low-mass star. The Boomerang Nebula represents a very brief, transitional phase in a star's life, a fleeting moment between being a red giant and becoming a full-fledged planetary nebula. The star at its heart is in the process of shedding its outer layers, but it's doing so in an extraordinarily violent and specific way. It isn't just gently puffing away its atmosphere. It is expelling gas at supersonic speeds, racing outward at over 160,000 kilometers per hour. This is the key to the incredible cold. In a principle of physics known as the adiabatic expansion effect, when a gas is allowed to expand rapidly into a near vacuum, it cools down dramatically. Think of it like using a compressed air duster. As the gas rushes out of the nozzle, it expands quickly and becomes intensely cold. The Boomerang Nebula is this principle operating on a stellar, almost unimaginable scale. The star is acting like a cosmic air conditioner, blowing a frigid wind into space so fast that the gas can't hold onto its heat, plunging the entire nebula to temperatures that approach the absolute lower limit of what is physically possible. The nebula's iconic shape, which gives it its name, further tells the story of this rapid expansion. The twin lobes of material that make it look like a boomerang are actually the outer edges of an ultra-cold, outflowing wind, shaped by a dense disk of dust and gas around the central star. This structure funnels the expelled material into two opposing jets, creating the distinct bipolar appearance. What we are witnessing is a star in the process of transforming itself, blasting its own essence out into the void, and in doing so, creating a pocket of the universe that is actively colder than the primordial afterglow of creation. This presents a fascinating cosmic paradox, a place of immense cold, born from the intense energy of a dying sun. It serves as a stunning reminder that the universe's extremes are not limited to searing heat and colossal explosions, but also extend into the realm of profound, silent, and absolute cold. Now, let's shift our focus from the profound cold of the Boomerang Nebula to an object of almost unnatural geometry and vivid color. Located about 2,300 light-years away in the constellation Monoceros, we find a nebula that seems to defy the typical, chaotic beauty of deep space. This is the Red Rectangle Nebula, and its name is a perfect description of its appearance. Through powerful telescopes, it doesn't look like a cloud or a ring, but rather like a set of glowing, crimson rungs on a cosmic ladder, forming an almost perfect X-shape that is unlike any other known structure in the heavens. It's so precise and angular that it looks less like a natural formation and more like a piece of abstract art or a structure deliberately placed in the void. The secret to this bizarre geometry lies in the dynamic heart of the nebula, a binary star system. At the center, two stars are locked in a tight orbital dance. One of them is a post-asymptotic giant branch star, a sun-like star in its final death throes that is actively shedding its outer layers into space. This is a common way for planetary nebulae to form. What's utterly uncommon here is how that expelled material is being shaped. Astronomers theorize that a thick, dense disk of dust and gas, a torus, surrounds this central binary pair. Imagine a giant cosmic donut wrapped tightly around the two stars. As the dying star ejects its atmosphere, this outflow cannot expand uniformly in all directions. Instead, it is funneled or pinched into two opposing cones shooting out from the poles of the dense torus. Because we are viewing this system almost directly from the side or edge-on, these two cones of gas appear to overlap, creating the distinct X-shaped structure that we see. It's a spectacular example of how the dynamics of a binary system can sculpt the final breath of a star into a form of breathtaking symmetry. Adding to its mystique is the nebula's intense and uniform red glow. This vibrant color doesn't come from the hot, ionized gas that lights up many nebulae. Instead, the red rectangle's crimson hue is emitted by something much more unusual: fluorescent hydrocarbon molecules. These are complex chains of carbon and hydrogen atoms, which are being excited by the intense ultraviolet light blasting from the very hot central white dwarf star. When this starlight hits the molecules, they absorb the energy and re-emit it as a specific, deep red light. This process, known as photoluminescence, is what gives the nebula its remarkable and consistent color. The presence of these molecules is a tantalizing clue, suggesting that the complex chemical building blocks for organic compounds are being forged in this stellar environment and sprayed out into the surrounding galaxy. This bizarre geometric object is therefore not just a marvel of celestial physics. It's also a potential factory for the prebiotic materials that are essential for life as we know it, a ruby-red enigma whispering secrets about the chemical richness of the cosmos. But just as we find perfect geometric shapes in the cosmos, we also encounter rhythms, cosmic clocks ticking in the most violent of places. Our next bizarre event takes us to a stellar mass black hole known as JURS 1915+105, a system located about 35,000 light-years away. This isn't just any black hole, it's a microquasar, a small-scale version of the supermassive monsters found at the centers of galaxies. And it has a peculiar habit. It beats with a steady, rhythmic pulse, a heartbeat detected in its X-ray emissions that repeats every 40 to 50 seconds. To find something as regular as a human heartbeat in the chaotic, destructive process of a black hole feeding is both astonishing and deeply revealing. The source of this rhythm is a cosmic dance of death. JURS 1915+105 is locked in a binary partnership with a regular star. The black hole's immense gravity is so powerful that it is constantly stripping material away from its companion. This stolen gas doesn't fall directly into the black hole. Instead, it forms a spinning, flattened disk of superheated matter known as an accretion disk. As this material spirals inward, it is compressed and heated to temperatures of millions of degrees, causing it to glow with intense X-rays. The heartbeat itself is thought to be created by a fascinating and violent process occurring at the very inner edge of this disk. Scientists believe that as material builds up in the disk, it reaches a critical threshold. Suddenly, the innermost region of the disk dumps a massive amount of material all at once into the black hole, releasing a tremendous flash of X-rays. The disk then empties out, briefly shutting off the flow before the process begins again, refilling and dumping in a stable, rhythmic cycle. It's a cosmic gulping mechanism, a predictable spasm in the black hole's feeding frenzy. What makes this phenomenon so extraordinary is its incredible stability. This heartbeat has been observed consistently for decades, since its discovery in the 1990s. In the universe, where celestial events are often unpredictable and transient, exploding once and fading away, the persistence of this pulse is remarkable. It provides astronomers with a rare and invaluable natural laboratory. By studying the precise timing and the properties of these X-ray pulses, scientists can probe the extreme physics of accretion right at the brink of a black hole's event horizon. They can test theories about how matter behaves under such incredible gravity, how energy is transported and released, and how the very fabric of space-time is twisted in these regions. This stable rhythm offers a controlled experiment, allowing us to understand the dynamics that power not only small microquasars but also their gigantic cousins, the quasars, which can outshine entire galaxies. This heartbeat in the void is more than just a curiosity. It is a steady drumbeat guiding our understanding of the most powerful engines in the universe. From the steady heartbeat of a feeding black hole, we now turn to a discovery so perplexing that astronomers initially thought it must be a glitch in their data. They are known as odd radio circles, or ORC, and they are exactly what their name suggests: enormous, faint, and perfectly circular rings of radio wave emission hanging in the depths of space with no clear explanation. When they were first identified in 2019 by the Australian Square Kilometre Array Pathfinder telescope, they were unlike anything ever seen before. They don't correspond to any visible object in optical, infrared, or X-ray light. They are ghostly halos that only appear when we tune our instruments to the radio part of the electromagnetic spectrum. They are not small, transient flashes. These are colossal structures, with some spanning a mind-boggling 1 million light-years across. To put that incomprehensible scale into perspective, a single ORC is so vast that it could completely envelop our entire Milky Way galaxy and the Andromeda Galaxy side by side with room to spare. They are, without exaggeration, among the largest single coherent structures ever identified in the universe. The mystery of the ORCs lies in their perfect isolation. When astronomers point other types of telescopes at the center of these circles, expecting to find a brilliant quasar, a colliding galaxy, or the remnant of a supernova, they often find nothing. Or more accurately, they sometimes find a perfectly normal-looking galaxy sitting quietly at the center, a galaxy that shows no signs of the colossal, energetic violence that would be required to create a bubble of radio waves of such staggering proportions. This complete disconnect between the immense energy of the radio ring and the apparent calm of the source at its heart is what makes ORCs one of the most captivating puzzles in modern astronomy. They are cosmic signatures without a clear author, immense ripples in a pond where no one can find the stone that was thrown in. So what could possibly create these ghostly circles? Scientists have proposed several theories, each one more dramatic than the last. One leading hypothesis suggests that ORCs are the aftermath of a truly titanic event, a starburst wind or a central supermassive black hole in a galaxy going through an intense, explosive phase of activity. In this scenario, a colossal shockwave of energy would be blasted out from the galactic center at nearly the speed of light. This wave would travel for millions of years, sweeping up intergalactic gas and electrons in its path and accelerating them to fantastic speeds. It is this shell of accelerated electrons spiraling in magnetic fields that would generate the synchrotron radiation we detect as a faint radio circle. We would be seeing the lingering echo of a cataclysm that occurred hundreds of millions of years ago, a fossilized bubble from a brief but incredibly violent period in a galaxy's life. Another compelling theory posits that ORCs might be the result of a phenomenon known as a termination shock. This could occur when the powerful jets from an active galactic nucleus, the superheated plasma beams shooting out from a supermassive black hole, abruptly slam into a much denser medium of intergalactic gas. The sudden deceleration would create a standing shockwave, a bright and immense ring at the precise point where the jet's energy is dissipated. This would be like seeing the radiant bow shock around a runaway star, but scaled up to an entire galactic system. There are even more exotic ideas on the table, including the possibility that ORCs are the throats of wormholes or the aftermath of a merger between two supermassive black holes. Events so energetic they could warp spacetime itself and create a spherical gravitational wave that somehow lights up in radio waves as it propagates. The existence of odd radio circles forces us to confront a humbling truth. Our map of the cosmos is still profoundly incomplete. We have built telescopes capable of seeing the faint glow of the first stars and mapping the cosmic web of dark matter. And yet, here in our own celestial backyard, these colossal, enigmatic structures have been hiding in plain sight, only revealing themselves when we looked in just the right way. They serve as a powerful reminder that the universe is still full of surprises, that there are entire classes of objects and phenomena waiting to be discovered, phenomena that challenge our existing categories and push us to develop new physics to explain them. Each new ORC detected is another piece of a cosmic jigsaw puzzle, a clue that we are on the verge of understanding a fundamental and previously invisible, aspect of how galaxies interact with the vast, empty spaces between them. Following the ghostly enigma of the odd radio circles, we encounter a star that has captivated both professional astronomers and the public imagination like no other. In the constellation Cygnus, roughly 1,400 light-years away, a seemingly ordinary star named KSE 8462852, more famously known as Tabby's star, began to reveal its profound strangeness. While most planets cause a star's light to dip in a regular, predictable rhythm as they transit, the data from the Kepler Space Telescope revealed something utterly unprecedented. Tabby's star doesn't just dim, it flickers and plunges in bizarre, erratic, and dramatic ways. Its light curves show dips of up to 22%, a staggering amount, far too large to be caused by any known planet. To block that much light, an object would need to be many times larger than the star itself. These dimming events are also completely aperiodic. They don't follow a schedule. Sometimes the star will fade slightly for a day. Other times it will plunge into a deep, complex dimming event that lasts for weeks, with multiple jagged drops and recoveries that look nothing like the clean, symmetrical curve of a planetary transit. The sheer scale of these dimming events immediately sent astronomers scrambling for an explanation, and the first theories were grounded in natural, if extreme, astrophysics. The leading hypothesis for years involved a massive, fragmented swarm of comets. The idea was that a family of millions of comets, perhaps disturbed by a passing star, could be on eccentric orbits around Tabby's star, and their dust and gas tails could be blocking the light in this irregular, clumpy way. While this could theoretically explain the irregular timing, many scientists found the explanation lacking. To create the deepest observed dips, the number of comets required would be almost implausibly vast, a swarm on a scale we see nowhere else in the cosmos. Other natural explanations followed, including the possibility of a recent planetary collision that had left a sprawling, chaotic cloud of debris in orbit, or that the star itself was surrounded by a warped, clumpy disk of interplanetary material that we were viewing almost edge on. Each theory had its merits, but each also faced significant challenges in fully explaining the complete set of bizarre observations. The inability of conventional astronomy to provide a perfect fit for the data inevitably led to a more speculative and far more sensational hypothesis, the alien megastructure theory. The notion, famously proposed by astronomer Jason Wright, was that the light pattern could be consistent with a vast, partially constructed swarm of energy-collecting satellites known as a Dyson sphere, built by an advanced extraterrestrial civilization. The irregular dimming could be explained by massive, rotating structures of different shapes and sizes passing in front of the star, blocking its light in a way that natural dust clouds or comets simply wouldn't. This idea, while thrilling, was always considered a last resort explanation, the one you turn to only after all natural possibilities have been exhausted. The scientific community largely remained skeptical, adhering to the principle that extraordinary claims require extraordinary evidence. Yet, the very fact that such an idea could be seriously debated in scientific circles highlights just how anomalous Tabby's star truly is. In the years since its discovery, an unprecedented citizen science and professional observing campaign has been mounted to monitor this star. The public, through projects like Planet Hunters, helped analyze vast amounts of data, and professional astronomers used everything from the Los Cumbres Observatory Global Telescope Network to the Swift Space Telescope to gather more clues. This intense scrutiny revealed another layer to the mystery. The star also appears to be undergoing a long-term secular dimming. Over the century of photographic plate observations and the last decade of precise photometry, Tabby's star has been getting steadily fainter. This combination of both short-term, violent dips and a long-term decline makes it a doubly puzzling object. So, where does the mystery stand today? The alien megastructure hypothesis has largely fallen out of favor, not because of a lack of imagination, but because of new, concrete data. Detailed observations across the electromagnetic spectrum, particularly in the infrared, have provided a crucial clue. If a solid object like an alien structure were blocking the light, the star would dim equally at all wavelengths. However, if fine dust is the culprit, it would block more blue light than red light. And indeed, observations show that Tabby's star dims more in blue light than in red, a clear signature of dust grains smaller than a micrometer in size. This strongly points toward a natural explanation involving circumstellar dust. The current most plausible model suggests that the star is surrounded by a vast, irregular cloud of extremely fine dust, likely the remains of a disintegrating moon or a shattered planetary body. The chaotic, unpredictable dimming events could then be caused by dense clumps and trailing streams of this debris passing in front of the star, with the long-term dimming caused by a more diffuse, overall cloud of this material spreading through the system. Yet, even with this convincing evidence for dust, Tabby's star is far from a solved case. The precise origin and dynamics of this dust cloud remain a topic of intense debate. What event could have created such an enormous quantity of fine dust? How does it maintain its clumpy, irregular structure without dispersing or coalescing? The star continues to be monitored, and it continues to surprise with new, unexpected dimming events occurring every now and then, ensuring that it remains one of the most actively watched and passionately debated objects in the sky. It stands as a powerful testament to the scientific process, a cosmic riddle that captivated the world, encouraged wild speculation, and was ultimately reined in by rigorous observation, yet still holds onto its core secrets, reminding us that sometimes the most intriguing answers simply lead to deeper, more nuanced questions. Just as we ponder the strange flickering of a single star, we now turn our attention to a force operating on a scale so immense it governs the motion of our entire galaxy and thousands of its neighbors. This is the mystery of the Great Attractor, a colossal gravitational anomaly located approximately 250 million light-years away in the direction of the Centaurus and Norma constellations. For decades, astronomers have known that the Milky Way is not drifting aimlessly through the cosmos. We are moving and moving fast at a staggering 2 million kilometers per hour. But this motion isn't random. It's a directed flow, a part of a vast cosmic current that includes our entire local group of galaxies, all being pulled relentlessly toward a specific point in space that we cannot directly see. This unseen focal point, this cosmic whirlpool, is what we call the Great Attractor. The primary challenge in studying this phenomenon is its profoundly inconvenient location from our earthly vantage point. It lies directly behind the crowded, dusty plain of our own Milky Way galaxy, in a region astronomers poetically call the zone of avoidance. This is not a place to be avoided out of superstition, but out of practical necessity. The disk of our galaxy is thick with immense clouds of interstellar gas and dust, which act like a cosmic fog bank, completely blocking our view in visible light. It is as if the most important landmark in our cosmic neighborhood is hidden behind an impenetrable, brightly lit billboard. For a long time, this zone was a literal blind spot in our maps of the universe, a blank space that frustrated our attempts to understand what was pulling us so powerfully. But astronomers are nothing if not ingenious, and they learn to see through the fog by switching their vision to wavelengths that can penetrate the dust. Just as airport security uses X-rays to see through luggage, astronomers turn to infrared and radio telescopes to peer through the galactic plane. Pioneering surveys like those conducted with the Parkes Radio Telescope in Australia began to systematically map this hidden realm. What they revealed was astonishing. Behind the veil of dust lay not just one, but a rich confluence of galaxy clusters, a massive overdensity of matter known as the Norma cluster. This cluster and the surrounding gravitational tapestry of what is now called the Laniakea supercluster, of which the Great Attractor is the central gravitational anchor, is the primary source of the pull. The Great Attractor isn't a single magical object. It is a focal point of mass, a vast gravitational well created by the combined pull of many thousands of galaxies, vast clouds of hot gas, and most significantly, an enormous amount of dark matter congregated in one region of space. The ongoing efforts to map this cosmic force are a testament to the evolving tools of cosmology. Modern missions like the Rosetta X-ray telescope are now scanning the zone of avoidance, not looking for starlight, but for the faint, million-degree glow of the hot gas that fills the spaces between galaxies in these massive clusters. By mapping this hot gas, scientists can trace the underlying gravitational skeleton of the universe, revealing the distribution of all matter, both seen and unseen. This has refined our understanding considerably. We now know that while the Great Attractor is a significant mass concentration, it is itself part of an even larger river of galactic motion. Our entire Laniakea supercluster is flowing toward an even more massive and distant structure known as the Shapley Attractor, the single largest concentration of mass in our nearby universe. So the pull we feel is a complex combination of local and global influences, a cosmic tug of war where the Great Attractor is a major waypoint, but not the final destination. This grand-scale dynamics forces us to confront the hierarchical nature of the cosmos. Galaxies are not isolated islands. They gather into groups which bind into clusters, which flow along filaments into superclusters, all drawn by the relentless pull of gravity toward the densest knots in the cosmic web. The Great Attractor is one such knot, a gravitational anchor in the vast ocean of space. Its ongoing study reminds us that to understand our own place in the universe, we must look not only at the stars above, but also through the obscuring dust of our own galactic backyard, mapping the invisible forces that have been guiding our cosmic journey for billions of years. While galactic collisions often result in the chaotic shredding of spiral arms, sometimes the cosmos produces a result of stunning, almost artificial perfection. This brings us to our 10th bizarre event, Hoag's object, a galaxy so geometrically perfect it looks less like a natural formation and more like a piece of celestial concept art. Discovered by astronomer Art Hoag in 1950, this non-typical galaxy lies about 600 million light-years away in the constellation Serpens. At first glance, it presents an almost unbelievable sight. A brilliant, round core of old, yellow stars is perfectly centered within a wide, detached ring of younger, blazing blue stars with a seemingly empty, utterly dark gap of space separating the two. It is a cosmic bullseye, a golden jewel box set within a sapphire band, floating in the void with a symmetry that challenges our understanding of how galaxies evolve. The immediate and most pressing question is, how does such a structure form without the familiar spiral arms or a central bar that connects the core to the outer disk? The leading theory points to a galactic collision, but not the head-on smash-up that might first come to mind. Instead, astronomers propose a scenario of a galactic trespass that occurred billions of years ago. The prevailing model suggests that a smaller, gas-rich dwarf galaxy once plunged directly through the heart of what was then a more ordinary, large spiral galaxy. This precise, bullseye collision would have sent immense gravitational shockwaves rippling through the larger galaxy's disk. These waves would have compressed the vast clouds of gas and dust orbiting in the outer regions, triggering a firestorm of new star formation in a precise, expanding ring. The inner regions of the original galaxy, meanwhile, largely survived the encounter intact, settling back into the serene, central core of old stars we see today. The trespassing dwarf galaxy itself would have been mostly torn apart and absorbed, its stars and gas contributing to the formation of the brilliant blue ring, leaving behind this beautiful, circular fossil of a long-ago cosmic encounter. What makes Hoag's object even more fascinating is the evidence that this ring-making process might be a repeating cycle. When you look closely at this galaxy, you discover an added layer of cosmic whimsy. Nestled within the dark channel between the yellow core and the blue outer ring, astronomers have identified another, much fainter and more distant ring galaxy, another potential hoax object visible right through the gap. This is not physically connected, it's a chance alignment, a glimpse of another ring galaxy billions of light years further away, seen through the window of the first. Yet its presence creates a breathtaking celestial tableau, a ring within a ring, hinting that while the formation of such perfect structures is rare, the underlying gravitational physics that creates them is a recurring theme in the universe. The existence of Hoag's object forces astronomers to confront the incredible diversity of galactic forms. It stands as a spectacular counterexample to the standard Hubble classification of galaxies as either spirals, ellipticals, or irregulars. It fits into none of these categories neatly, belonging instead to a very rare class known as ring galaxies. Its pristine condition suggests that it has been relatively undisturbed since its formative collision, offering a unique, frozen-in-time laboratory for studying the long-term effects of such immense gravitational interactions. The stark segregation of stellar populations, the old stars in the core and the young stars in the ring, provides a clear timeline of the galaxy's history, a story written in starlight. This cosmic bullseye is more than just a pretty picture. It is a dynamic relic, a permanent record of a violent past that resulted in one of the most serene and perfectly balanced structures we have ever discovered in the deep sky. Just when we thought we had catalogued the final acts in a star's life, the cosmos reveals a new character in the stellar drama, one that behaves less like a brilliant beacon and more like a reclusive cosmic dragon guarding a hoard of cosmic dust. Enter the old smoker stars, a newly identified type of ancient red giant lurking in the crowded heart of our galaxy. These aren't the predictable, steady burning stars we're used to. They are enigmatic elders that spend decades, even centuries, in a state of quiet calm before suddenly, and without apparent warning, exhaling colossal clouds of sooty smoke and dust. This outburst is so immense it can shroud the entire star, causing its visible light to dim dramatically for months or even years, as if a celestial hand has slowly closed around it before eventually opening again to let the light return. The discovery of these stellar phantoms was a classic case of scientific serendipity. Astronomers were using the Visible and Infrared Survey Telescope in Chile to search for newborn stars, the vibrant and energetic youngsters known as protostars, when they kept noticing a different kind of object altogether. They found numerous old, red giant stars that would remain stable for long periods, then suddenly fade by a staggering 40 to 100% in visible light, only to brighten again to their original state much later. The key to understanding this bizarre behavior was found in the infrared part of the spectrum. While the star's visible light was being blocked, its infrared glow would often increase. This is the telltale signature of dust. The smoke these old stars are puffing out is composed of tiny particles of carbon-rich compounds and silicate dust. This newly formed cloud absorbs the star's intense visible light, heating up in the process and re-radiating that energy as a stronger infrared glow, effectively hiding the star in plain sight while revealing its secret in a different light. So, what triggers this strange, smoky behavior in such an advanced stage of stellar life? The leading theory is a process known as a thermal pulse. In the final stages of a sun-like star's life, after it has expanded into a red giant, its interior becomes a series of layered shells burning different elements. Occasionally, a shell of helium just above the star's core can ignite in a burst of fusion that is not stable, but rather a violent, runaway thermal explosion. This pulse sends a powerful shockwave rippling outward through the star's enormous, distended atmosphere. The pulse doesn't blow the atmosphere away entirely. Instead, it lifts vast quantities of material from the star's outer layers, carrying it to a region where the temperature is just right for atoms to condense into solid dust grains, much like soot forming in a candle flame. The star isn't exploding, it's coughing, and each cough propels a new wave of cosmic soot into the surrounding space. This newly identified phase of stellar evolution has profound implications for the chemical enrichment of our galaxy and indeed the entire universe. Red giant stars are the primary cosmic forges for many of the heavier elements essential for life, such as carbon, nitrogen, and oxygen. They create these elements through nuclear fusion in their cores and then dredge them up to the surface through complex convective processes. The old smokers appear to be a crucial and previously overlooked delivery mechanism for these elements. By packaging these newly forged heavy elements into solid dust grains and then gently puffing them out into the interstellar medium, these stars are effectively seeding the galaxy with the raw materials for future planets and potentially life itself. Unlike a supernova, which blasts material out at tremendous speeds, the slow, gentle ejection from an old smoker allows these fragile dust grains to survive intact. They can then become part of the giant molecular clouds that will one day collapse to form new stellar systems, carrying with them the essential ingredients for rocky planets and organic chemistry. These seemingly lethargic stars, then, are not just celestial curiosities. They may be among the galaxy's most important and efficient gardeners, quietly sowing the seeds for future cosmic generations. Moving from the smoky outbursts of ancient stars, we venture into the profound and chilling darkness between the stars, where a different kind of celestial wanderer drifts in perpetual exile. These are the rogue planets, worlds without a sun, cast adrift from their stellar families to roam the galactic void alone. Astronomers now estimate their numbers are staggering, potentially numbering in the billions or even trillions within our Milky Way galaxy alone, far outnumbering the stars themselves. Picture a planet like Jupiter or even Earth, but one that knows no day, no year, and no warmth. Its sky is an eternal, star-studded blackness, a vista of unblinking lights with no central sun to provide light, heat, or the anchor of a seasonal cycle. This is not a rare anomaly, it is a fundamental and surprisingly common part of our cosmic architecture. So how does a planet find itself so utterly alone? A primary theory points to a violent and chaotic origin story within young solar systems. In the frenzied first few million years after a star forms, its planetary disk is a crowded, gravitational free-for-all. Protoplanets and planetesimals jostle for position, their orbits not yet settled into the stable, well-spaced patterns we see in our mature solar system. During this turbulent era, close gravitational encounters between young, massive planets can be catastrophic. A smaller world, like an Earth, could be gravitationally slingshotted out of the system entirely by a close pass from a Jupiter-sized giant. In other scenarios, a near miss between two gas giants can fling one, or even both, out into the interstellar deep, a cosmic game of pinball with the highest stakes. There is also the possibility that some rogue planets form on their own, in the same way stars do from the direct collapse of a small, isolated cloud of gas and dust. These would be the true orphans of the galaxy, born in darkness and destined to never know the light of a parent star. Detecting these dark wanderers is one of the most formidable challenges in modern astronomy. Since they emit no light of their own and reflect no starlight, they are effectively invisible to traditional survey methods. The key to finding them lies in a subtle and rare phenomenon known as gravitational microlensing. When a rogue planet drifts almost perfectly in front of a distant background star, its gravity acts as a tiny lens, bending and focusing the star's light for a brief period. This causes the background star to momentarily brighten in a very specific, predictable way. The event is incredibly fleeting, lasting from a few hours for an Earth-mass planet to a couple of days for a Jupiter-sized world. Catching these events requires monitoring hundreds of millions of stars continuously, a task undertaken by sophisticated surveys like Poland's optical gravitational lensing experiment and Korea's microlensing telescope network. Each successful detection is a triumph of patience and precision, a brief flash of data that confirms the presence of a frozen, solitary world. This leads us to one of the most mind-bending questions in all of astrobiology. Could life exist on a planet forever frozen in the darkness of interstellar space? At first glance, the idea seems preposterous. The surface of a rogue planet would be a cryogenic wasteland, with temperatures plummeting to near absolute zero, locking any atmosphere into a frozen solid. But life on Earth has repeatedly shown us that it is incredibly tenacious, thriving in places we once thought utterly inhospitable, around superheated hydrothermal vents at the bottom of the ocean, or deep within isolated radioactive rock formations. The most compelling scenario for life on a rogue planet does not involve its surface, but what might lie beneath. Consider a rogue world that began its life as a watery planet in the outer reaches of its solar system, a place like Jupiter's moon Europa or Saturn's Enceladus. When ejected, its icy surface would freeze into a thick global crust, perhaps dozens of kilometers thick. But deep below, the heat from the planet's radioactive core, left over from its formation, could persist for billions of years. This internal heat could be sufficient to maintain a vast, global subsurface ocean of liquid water, trapped between the frozen outer shell and a rocky, heated interior. In such an environment, the conditions could be strikingly similar to the deep oceans of Europa. There would be no sunlight for photosynthesis, but life could potentially draw energy from chemical reactions, a process known as chemosynthesis. Hydrothermal vents on the ocean floor, fueled by the planet's internal heat, could provide a constant supply of energy-rich chemicals, just as they do on Earth. In this perpetual, warm, dark ocean, an entire ecosystem could theoretically exist, completely independent of any star, thriving in a world of its own making. These potential biospheres would be the most isolated in the universe, sealed away under a shield of ice, traveling through the galaxy on a journey that could last for trillions of years, outliving every star that ever shone. The existence of such life would fundamentally redefine the habitable zone, expanding it from the narrow band around stars to include the entire, vast and dark expanse of interstellar space itself. But our journey into the cosmic pantry doesn't end with the raw elements forged in stars. We now venture into a region of space that acts as a sprawling, interstellar kitchen, whipping up complex organic molecules. Near the crowded heart of our Milky Way, about 390 light-years from the supermassive black hole Sagittarius A, floats a colossal giant molecular cloud known as Sagittarius B2. This isn't just a simple cloud of hydrogen gas. It is one of the largest and most chemically rich reservoirs of its kind in our galaxy, a veritable factory for cosmic chemistry. And within its frigid, dark depths, astronomers have made a stunningly sweet discovery: the presence of glycolaldehyde, a simple sugar molecule. This is not just a curiosity, it's a direct detection of one of the fundamental building blocks of the RNA and DNA that form the basis of all known life. Finding this cosmic candy in such a hostile, radiation-bathed environment is a profound clue that the universe may be inherently probiotic, predisposed to cooking up the ingredients for life wherever the right conditions exist. The process of how these delicate molecules form in the cold vacuum of space is a fascinating piece of cosmic alchemy. It defies our everyday intuition, which suggests that complex chemistry requires warm, liquid environments like those found on Earth. Instead, the formation happens on the surfaces of minuscule, frigid dust grains that are floating within the cloud. These dust particles, often coated in a mantle of water ice, act as tiny chemical laboratories. Simple, abundant atoms and molecules like carbon monoxide, formaldehyde, and hydrogen slowly drift through the cloud and stick to these cold dust grains. Once anchored to a surface, they lose a little energy and can slide around. When they bump into each other, guided by the unique landscape of the ice mantle, they can link up through a series of surface-mediated reactions. It's a slow, patient process, but in the dense core of a cloud like Sagittarius B2, there is an immense amount of raw material and time, millions of years, for these reactions to build molecules of surprising complexity, atom by atom, right on the surfaces of icy dust motes. The significance of this discovery extends far beyond the novelty of sugar in space. Glycolaldehyde is a key molecule in the chemistry of life as we understand it. It plays a central role in the Formose reaction, a pathway that can lead to the formation of ribose, which is the R in RNA. Ribose is the sugar phosphate backbone that forms the structural spine of the RNA molecule, a molecule widely believed by scientists to have been a crucial stepping stone in the origin of life on Earth. The implication is staggering. The very scaffolds for genetic material might be being manufactured in deep space, long before a planet even forms. This means that when a new planetary system coalesces from a cloud like Sagittarius B2, it could already be seeded with these pre-made organic ingredients. The protoplanetary disk that gives birth to planets would be laced with these molecules, which could then be delivered to the surfaces of young, watery worlds via comets and asteroids, providing a potential head start for the emergence of life. This discovery forces a major shift in our perspective on life's origins. It moves the question from how could life begin from simple chemicals on Earth, to how far did the preparation for life get in space before it even reached a planet? The universe appears to be a far more capable chemist than we once imagined, conducting sophisticated organic synthesis in the most unlikely of places. The dense molecular clouds that pepper our galaxy are not just stellar nurseries. They are also chemical nurseries, routinely producing a rich inventory of molecules that include amino acids, the components of proteins, and now the sugars essential for genetics. The existence of this cosmic candy in Sagittarius B2 strongly suggests that the fundamental building blocks of biology are not a rare, earthly fluke, but a common and widespread cosmic resource, dramatically increasing the probability that the universe is teeming with the raw ingredients necessary for life to begin elsewhere. But if the quiet patience of old smokers and rogue planets represents one end of the stellar spectrum, our next phenomenon catapults us to the opposite extreme, a class of stars so massive, volatile, and violently unstable that they seem to be living on borrowed time. These are the luminous blue variables, and the most famous and terrifying example of this breed is Eta Carinii, a celestial behemoth located about 7,500 light-years away in the constellation Carina. We are not talking about a star that gently ages. We are talking about a star that is actively and spectacularly tearing itself apart. To understand the sheer scale of Eta Carinii, you must first abandon any concept of a normal star. This is a hypergiant, a stellar monster containing the mass of at least 100 of our suns, and it burns with a luminosity millions of times greater. It is so profoundly massive that its own gravity is barely able to hold it together. The outward pressure from its frantic nuclear fusion battles constantly against the inward crush of its own immense weight, creating a state of perpetual, precarious imbalance. A luminous blue variable like Eta Carinii doesn't just shine. It quakes, shudders, and periodically experiences catastrophic outbursts as it struggles against its own self-destruction. This isn't a stable star, it is a star in its final, furious death throes, a prelude to one of the most energetic explosions in the universe, and we have witnessed its fury firsthand. In the 1840s, Eta Carinii underwent what astronomers now call the Great Eruption. For a brief period, it became the second brightest star in the entire night sky, outshone only by Sirius despite its vast distance. It wasn't a true supernova. The star somehow survived. Instead, it was a colossal, non-terminal eruption, a titanic belch of stellar material where the star ejected an estimated 10 to 15 times the mass of our entire sun into space. This cataclysmic event created the magnificent and iconic Homunculus Nebula, a bipolar cloud of expanding gas and dust that now envelops the star, When viewed with modern telescopes like Hubble, the homunculus appears as a stunning, ghostly figure, a pair of glowing lobes that are the fossilized remnants of that single 19th century outburst. The material is still expanding outward today, a permanent monument to the star's violent instability. The cause of this incredible eruption is still a subject of intense research, but the leading theory points to a ferocious battle between radiation pressure and gravity. In a star this massive, the light it produces is so intense that the photons themselves exert a significant outward push. Scientists believe that Eta Carinii may have approached what is known as the Eddington limit, the point where the outward radiation pressure from the star's core exactly balances the inward pull of gravity. At this threshold, the star becomes critically unstable. Its outer layers become so energized by the radiation that they are effectively levitated, no longer bound firmly by gravity. A slight nudge, perhaps from pulsations deep within the star's interior, can then blow these enormous portions of the atmosphere clean off into space, like a sail being torn from its mast by a hurricane. It's a stellar identity crisis of the highest order, where the star's own light becomes the engine of its self-destruction. Compounding this inherent instability is the fact that Eta Carinii is not one star but two. It is a binary system with a smaller, yet still immensely powerful, hot companion star whirling around the primary hypergiant in a highly elliptical 5.5-year orbit. This duet adds a layer of dramatic periodic violence to the system. When the two stars make their closest approach, or periastron, their stellar winds blasting outward at millions of kilometers per hour collide with the force of a continuous explosion. This collision creates a deafening roar in X-rays that we can detect from Earth, and it is believed that these close encounters may trigger further mass loss and eruptions, periodically stressing the already fragile primary star to its absolute limits. Today, Eta Carinii remains one of the most closely watched objects in the sky because astronomers are universally convinced that its days are numbered. It is a prime candidate to explode as a supernova or even as a hypernova, a blast so energetic it could unleash a gamma-ray burst. The star could detonate in 1,000 years, or it could happen before this sentence is finished. There is no way to predict it. When it finally does go, it will be a spectacular event for humanity. For a period of weeks or months, it could become as bright as the full moon, visible even in broad daylight, casting shadows on the Earth at night. It will be a safe but utterly breathtaking cosmic firework, a final, defiant act from a star that has been fighting a losing battle with itself for millennia. Eta Carinii serves as a stark and brilliant reminder that the universe is not only capable of creating monsters, but that their spectacular deaths are an integral part of the cosmic cycle, forging the heavy elements that will one day seed new stars, new planets, and perhaps new life. As if the gravitational pull of the Great Attractor weren't enough of a cosmic mystery, astronomers have stumbled upon something even more profound and unsettling, a motion so vast and inexplicable that it seems to challenge the very foundations of modern cosmology. We now turn to the phenomenon known as the dark flow. Imagine you've meticulously mapped every continent, every mountain range, and every ocean trench on Earth, and you understand the flow of all the planet's rivers. Now you notice that the entire planet itself is drifting, not just rotating or orbiting, but being pulled through the solar system in a specific, coherent direction by something you cannot see. This is the scale of the dark flow mystery, but applied to the entire observable universe. It is the controversial finding that not just a few galaxies, but entire clusters of galaxies, each containing thousands of individual galaxies, appear to be streaming in a uniform, coordinated direction at phenomenal speeds of millions of kilometers per hour, a motion that cannot be accounted for by any known structure or force within our visible cosmos. The evidence for this startling motion comes from a very clever analysis of the cosmic microwave background radiation, the ancient afterglow of the Big Bang that fills all of space. This radiation is the oldest light we can see, and it should be remarkably uniform in all directions, a perfect relic of the universe's hot, dense beginning. However, as galaxy clusters move at incredible speeds through space, they interact with this radiation in a subtle way known as the kinematic Sunyaev-Zeldovich effect. The hot gas in these clusters scatters the CMB photons, and if the cluster is moving, it imparts a tiny, measurable shift to the energy of those photons, much like the Doppler effect changes the pitch of a passing siren. By meticulously studying this effect in the WMAP and later the Planck satellite data, a team of scientists led by Alexander Kashlinsky found a shocking pattern. They discovered that hundreds of distant galaxy clusters were all showing a consistent velocity vector, all moving toward a specific patch of sky between the constellations Centaurus and Vela. This wasn't a random drift, it was a coordinated flow, a cosmic river on the grandest possible scale. The truly baffling part of this discovery is that this motion persists at distances so vast that, according to our standard model of cosmology, it should be impossible. The known universe is governed by the principle of isotropy, meaning it should look roughly the same in all directions, and the gravitational influence of matter should be local. The gravitational tug of the Great Attractor or the Shapley supercluster can explain our local motion, but the dark flow appears to affect clusters billions of light years away, far beyond the reach of any known cosmic structure's gravitational pull. Within our observable universe, there simply isn't enough concentrated matter in that direction to account for such a coherent, long-range stream. This is why the phenomenon was dubbed the dark flow. Its cause is invisible and unknown, just like dark matter and dark energy, but its implications are arguably even more staggering. This leaves scientists with a truly mind-boggling possibility, one that pushes the boundaries of physics itself. The leading theoretical explanation is that the dark flow is the gravitational imprint of something that lies beyond our observable universe. According to the theory of cosmic inflation, the universe we can see is just a tiny bubble in a much vaster and potentially infinite multiverse. If this is true, then the space beyond our cosmic horizon is not empty. It could be filled with other bubble universes, each with its own distinct properties and distribution of mass. The unimaginable concentration of matter in one of these external universes could be exerting a gravitational pull on our entire local cosmos, creating the coherent stream we detect as the dark flow. We would be like fish in a pond, suddenly becoming aware that the entire pond is flowing because of the gravitational pull of a mountain in a distant, unseen continent. Of course, a finding this extraordinary is met with intense scrutiny and healthy skepticism within the scientific community. Some researchers have questioned the statistical significance of the result, suggesting that the observed signal could be an artifact of incomplete data processing or an unaccounted for systematic error in the measurements of the cosmic microwave background. The Planck satellite, which provided the most precise map of the CMB to date, did not confirm the dark flow with the same level of confidence, though it also didn't completely rule it out. The debate continues, driving the need for more precise observations from future missions. The very existence of this controversy highlights a critical point in science. The most profound discoveries are often those that challenge our most deeply held assumptions. The dark flow forces us to confront the humbling possibility that our entire observable universe, with its hundreds of billions of galaxies, might not be a self-contained island, but merely one piece of a much grander and utterly alien cosmological structure. From the coordinated flow of entire galaxy clusters, we turn now to a single, ancient point of light much closer to home, a star whose very existence seemed for a time to break the universe. This is the Methuselah star, officially catalogued as HD 140283, a faint, unassuming star in the constellation Libra that became the center of a monumental cosmic paradox. When astronomers first managed to measure its age with the Hubble Space Telescope over a decade ago, the results were nothing short of shocking. Their initial calculations placed the star's age at around 14.5 billion years old. This was a huge problem because the most precise measurements of the universe's age, derived from the cosmic microwave background, peg it at approximately 13.8 billion years. According to those early numbers, this star would have been born hundreds of millions of years before the universe even existed, a logical impossibility that sent theorists scrambling and threatened to upend our fundamental understanding of cosmology. The key to this star's incredible age lies in its composition. HD 140283 is a rare and ancient relic known as a population 2 star. To understand what that means, we need to think about cosmic generations. The very first stars to ignite after the Big Bang, called population 3 stars, are believed to have been colossal, short-lived giants made almost entirely of hydrogen and helium, the primordial elements forged in the first few minutes of the universe. When these pioneers exploded as supernova, they seeded the cosmos with the first heavier elements like oxygen, carbon, and iron. The Methuselah star is a member of the next generation. It formed from gas that had been enriched by those first supernova, but it contains only a tiny amount of these heavier elements, far less than 1% of what is found in our Sun. This metal-poor composition is the stellar equivalent of a birth certificate. It tells us this star is a true senior citizen of the galaxy, forming when the universe was still in its cosmic infancy, before many heavy elements were widely available. So, how did we end up with an age that seemed to defy the cosmos? The uncertainty wasn't in the star's chemistry, but in the incredibly delicate and complex process of stellar dating. Astronomers determine the age of a star like this by measuring its properties with extreme precision: its brightness, its temperature, and its exact chemical composition. They then feed this data into sophisticated computer models of how stars evolve. The initial age estimate of 14.5 billion years came with a significant margin of error, a window of plus or minus 800 million years. This meant the star's true age could have been as low as 13.7 billion years, which would have fit comfortably within the universe's age of 13.8 billion. The headline-grabbing number was at the very upper limit of that uncertainty range. It was a best guess that pushed the boundaries of possibility, highlighting the immense challenges of measuring something so fundamental. In the years since that bombshell announcement, astronomers have been refining their measurements, incorporating new data to solve the paradox. A major breakthrough came from even more precise observations of the star's distance, made by the European Space Agency's Gaia mission. Knowing a star's exact distance is absolutely critical for determining its intrinsic brightness, which is a key input for the stellar models. The updated Gaia data allowed scientists to recalculate the star's luminosity with far greater accuracy. When this new, sharper data was plugged into the models, the estimated age of the Methuselah star shifted. The most recent calculations now place its age at around 13.7 billion years, give or take a few hundred million. This revised figure sits neatly within the age of the universe, resolving the paradox. The star is still profoundly ancient, the oldest known individual star whose age we can measure, but it is no longer older than the universe itself. The story of the Methuselah star is far more than a tale of a corrected error. It is a powerful lesson in the scientific process and a breathtaking glimpse into the deepest past. This star is a time capsule from the dawn of creation. Its existence confirms that the first generations of stars formed with astonishing speed after the Big Bang. The universe was only a few 100 million years old, a mere infant when this star ignited. Its survival for over 13 billion years is a testament to its modest mass. It was just small enough to burn its fuel slowly and steadily, rather than exploding violently after a short, brilliant life like its massive population 3 ancestors. By studying its specific blend of elements, we are effectively conducting an archaeological dig into the conditions of the early cosmos. learning about the yields of the very first supernova. The Methuselah star stands as a living fossil, a direct link to a time when the universe was young, dark, and just beginning to light up with the first sparks of stellar fire, a reminder that our cosmic history is written in the light of the oldest stars still shining today. While we often picture a supernova as a star tearing itself apart in a blinding flash of self-destruction, the cosmos has a way of surprising us with a quieter, more insidious form of stellar death. Our 17th bizarre event takes us to the peculiar case of supernova IPTF14 GQR, an explosion that defied all expectations. When astronomers spotted it in 2014, they witnessed the characteristic brightening of a dying star, but something was profoundly wrong. The flash was unusually brief and faint, and when the light faded, there was an astonishing lack of debris, the expanding cloud of stellar material that normally forms a beautiful, long-lasting remnant. This was an empty supernova, a cosmic whimper that has earned it the title of an ultra-stripped supernova, a star that seemed to explode with almost nothing left to give. The mystery of this underwhelming blast points directly to a cosmic theft occurring long before the final detonation. The leading theory paints a dramatic picture of a binary star system locked in a gravitational dance of life and death. In this scenario, the star destined to explode, a massive helium core, was not alone. It had a voracious companion, likely a dense neutron star or another compact object, orbiting dangerously close. For millions of years, this companion acted as a stellar vampire, using its powerful gravity to slowly and systematically siphon away the hydrogen-rich outer envelope of the doomed star. This wasn't a quick process. It was a patient, relentless stripping away of the star's own atmosphere, pulling the material into an accretion disk around the companion or flinging it out into space entirely. By the time the star's core was ready to collapse, nearly all of its outer layers had already been stolen. The star was left a naked core, a bare, massive ball of helium and heavier elements with virtually no hydrogen left to blow away in a traditional, spectacular explosion. This pre-explosion theft completely changed the nature of the supernova event itself. In a typical core collapse supernova, the rebounding shockwave from the collapsing iron core has to plow through a massive, extended envelope of stellar material. This collision is what creates the brilliant, long-lasting light show and the expansive debris cloud we associate with these cosmic explosions. But for IPTF14 GQR, that envelope was gone. When the core finally collapsed, the resulting shockwave had almost nothing to push against. It burst out into a near vacuum, resulting in a quick, short-lived flash of light and a minimal ejection of mass. The entire explosive event was over almost as soon as it began, a fleeting, low-energy burst that would have been easy to miss entirely. It was the supernova equivalent of a firecracker instead of a bomb, its power drastically reduced because the fuel for a grander display had already been taken. The discovery of this ultra-stripped supernova is more than just a curious oddity. It provides a crucial missing link in our understanding of how some of the universe's most exotic binary systems are born. Astronomers have long detected tight binary systems where two neutron stars orbit each other, spiraling closer and closer until they collide in events that shake the very fabric of space-time, emitting gravitational waves and creating heavy elements like gold and platinum. The question has always been, how do such systems form without the supernova explosion from the first neutron star kicking the pair apart? The ultra-stripped supernova offers a perfect solution. Because the exploding star has been stripped of almost all its mass, the supernova kick, the recoil from an asymmetrical explosion, is incredibly weak. This gentle kick is insufficient to disrupt the binary system, allowing the newly formed neutron star to remain gravitationally bound to its companion. The pair continues its cosmic dance, destined for a future merger billions of years down the line. This bizarre, empty explosion is therefore a key creator of the very binary systems that allow us to study the ripples in space-time and the origin of the universe's most precious elements. Yet for all the violence of an ultra-stripped supernova, the stellar corpse it leaves behind can be the source of even greater cosmic fury. We now arrive at the 18th bizarre event, a phenomenon born from one of the most extreme objects in existence, the magnetar. Picture the core of a massive star, a volume larger than our Sun, crushed by gravity into a perfect sphere just 20 kilometers across, the size of a city. This is a neutron star, a single sugar cube of its matter weighing as much as a mountain. Now take that already unimaginable object and imbue it with a magnetic field so powerful it defies all analogy. A magnetar's magnetic field is 1,000 trillion times stronger than Earth's. If one were located halfway between the Earth and the Moon, its magnetic pull would effortlessly strip the data from every credit card on the planet. This is not just a strong magnet, it is a fundamental force of nature incarnate, and it places the star's solid crust under unimaginable, relentless strain. This strain is the engine for one of the most catastrophic events known to astrophysics, the starquake. A neutron star is not a uniform fluid. It is thought to have a solid, crystalline crust of iron nuclei, a lattice so dense it is harder than diamond. This crust is locked onto the star's insanely powerful magnetic field, which is not static but constantly evolving and twisting. As the magnetar ages, its incredibly powerful magnetic field exerts immense stress on this solid crust, bending and warping it like a slab of metal under a hydraulic press. Eventually, the crust can no longer withstand the pressure. It fractures. This is a starquake, but to call it a quake is like calling a supernova a spark. When the crust of a magnetar snaps, it releases more energy in a fraction of a second than our Sun will emit over 100,000 years. This catastrophic cracking causes a massive rearrangement of the star's magnetic field, a process that unleashes a blinding flash of high-energy radiation, primarily in the form of gamma rays and X-rays. The effects of such an event are so profound they can ripple across the galaxy and touch our own world. On December 27, 2004, a wave of radiation from a magnetar located 50,000 light-years away struck Earth's upper atmosphere. For 0.2 of a second, this single object outshone the full moon, making it the brightest transient event ever recorded from outside our solar system in the history of human astronomy. It was a giant flare from a starquake, and its impact was immediate. It violently ionized the upper layers of our atmosphere, overloading satellite sensors and significantly disrupting long-wave radio communications across the globe. If such an event were to happen much closer, say within 10 light-years, the results would be apocalyptic. The gamma-ray blast would not only destroy our ozone layer, exposing all life to deadly ultraviolet radiation from the Sun, but it could also trigger a wave of chemical reactions in the atmosphere, potentially causing acid rain and a prolonged extinction-level event. Fortunately, the nearest known magnetar is much further away, but the event of 2004 serves as a stark reminder of the violent interconnectedness of our cosmos. Beyond their terrifying power, these starquakes provide humanity with a unique and invaluable natural laboratory. The vibrations that ripple through the neutron star's body after a quake, much like seismic waves on Earth, carry precise information about the star's internal structure. By studying the oscillations in the X-ray glow that follow a giant flare, astronomers can perform a kind of stellar seismology. The way the star rings after being struck tells us about the density, pressure, and composition of matter at its core, states that are impossible to recreate in any laboratory on Earth. We are talking about densities where atomic nuclei are pressed together, forming exotic soups of neutrons, protons, and potentially even stranger states of matter like a superfluid of neutrons or a crystal of subatomic particles. Each starquake is like striking a bell made of ultra-dense matter. By listening carefully to its peal, we can begin to understand the physics that governs the most extreme states of matter in the universe, pushing the boundaries of our knowledge to the very edge of what is physically possible. Even as we unravel the mysteries of stellar corpses and galactic flows, a more fundamental disagreement is brewing among cosmologists, one that strikes at the very heart of our understanding of the universe's evolution and ultimate fate. This is the Hubble tension, a stubborn and growing discrepancy that has escalated from a minor puzzle into a full-blown crisis in cosmology. At its core, the tension is about a single, crucial number, the Hubble constant. This value represents the current expansion rate of the universe, telling us how fast galaxies are receding from us for every megaparsec of distance. It is the most important number in cosmology, the key to determining the age of the universe, its past history, and its future destiny. The problem is, we now have two supremely confident, yet stubbornly incompatible, ways of measuring it, and they refuse to agree. One path to measuring the Hubble constant is to look at the very early universe, using the afterglow of the Big Bang itself as our guide. This is the cosmic microwave background, the faint microwave radiation that permeates all of space, a snapshot of the universe when it was just 380,000 years old. Meticulous observations from space-based telescopes like Planck have mapped this radiation with exquisite precision. By analyzing the tiny temperature fluctuations in this background, scientists can apply the well-tested laws of physics to run the cosmic film forward, calculating how the universe should have evolved over 13.8 billion years to arrive at its present state. This early universe method gives us a very precise and consistent value for the Hubble constant. It suggests a universe that is expanding at a rate of about 67 kilometers per second for every megaparsec of distance. This value fits perfectly within our standard model of cosmology, known as lambda cold dark matter, which includes the known effects of dark matter and dark energy. The other path is to measure the expansion directly in our local, modern universe. This late universe approach relies on building what astronomers call the cosmic distance ladder. It's a step-by-step process that starts with relatively close objects like Cepheid variable stars, whose known intrinsic brightness allows us to calculate their distance accurately. We then use these as calibrators for brighter distance markers like Type Ia supernova, which can be seen much further across the cosmos. By meticulously measuring the distances to these far-off supernova and comparing them to the redshift of their host galaxies, which tells us how fast they are moving away, we can directly measure the current expansion rate. This painstaking work, championed by teams like the one using the Hubble Space Telescope, yields a different answer. It points to a Hubble constant of around 73 kilometers per second per megaparsec. The difference between 67 and 73 may seem small, but the precision of each measurement is so high that the chance this discrepancy is a simple error is now less than 1 in a million. It is a real and significant conflict. This isn't just a minor accounting error, it is a fundamental rift in our cosmic ledger. If both methods are correct, then our standard model of cosmology, which has been spectacularly successful for decades, must be missing something crucial. The early universe, as seen by Planck, and the modern universe, as measured by Hubble, are telling two different stories about how cosmic expansion has played out. This has sent theorists on a thrilling hunt for new physics that could bridge the gap. Perhaps dark energy, the mysterious force driving accelerated expansion, is not a constant as we've assumed. Maybe it has evolved over time, growing stronger in the recent cosmic past, which would explain why the local universe is expanding faster than our extrapolation from the early universe predicted. This would mean the fate of the cosmos is even more dramatic than we thought, potentially leading to a big rip where the fabric of spacetime itself is torn apart. Other proposals are even more exotic. Could there be a new, previously unknown type of relativistic particle that flooded the early universe, subtly changing how it evolved? Or perhaps dark matter has properties more complex than simply being cold and non-interacting. Maybe it can interact with itself or with dark energy in ways we haven't yet conceived. The profound implication of the Hubble tension is that it highlights a potential flaw in our most basic understanding of the cosmos. For years, the lambda cold dark matter model has been our cosmic rulebook, successfully explaining everything from the large-scale structure of the universe to the abundances of the light elements. Now, this single, persistent discrepancy suggests the rulebook is incomplete. It is a powerful reminder that science advances most dramatically, not when all the pieces fit neatly, but when they don't. The Hubble tension is an open door, an invitation to a deeper layer of reality, pushing us to discover new forces, new particles, or new principles that govern the evolution of everything we see. It is a living, breathing scientific debate, a cosmic puzzle that assures us the universe still has profound secrets to reveal, and that our journey to understand it is far from over. While we grapple with the large-scale mysteries of cosmic expansion, a completely different kind of messenger is arriving from the most violent corners of the universe, offering a unique glimpse into processes hidden from conventional telescopes. This brings us to our 20th bizarre event, the detection of cosmic ghosts. Deep within the pristine ice of the South Pole, buried under a kilometer of ancient transparent glacier, lies one of the most extraordinary scientific instruments ever conceived, the IceCube Neutrino Observatory. It is not a traditional telescope with lenses and mirrors. It is a colossal particle detector designed to catch glimpses of the most elusive entities in the cosmos, high-energy neutrinos, often called ghost particles. To understand why catching a ghost is such a monumental achievement, you need to appreciate the nature of a neutrino itself. These are subatomic particles, but they are unlike any other. They are nearly massless, carrying no electric charge, and they interact with ordinary matter so rarely that they can pass through light years of lead as if it weren't even there. Trillions of neutrinos from the sun are streaming through your body every second of every day, completely unnoticed, leaving no trace. This ghostly nature is both a challenge and a blessing. Because they are not deflected by magnetic fields and rarely collide with anything, they travel in perfectly straight lines across the universe, carrying information directly from their violent birthplaces, unaltered and uncorrupted. They are the ultimate cosmic couriers, but building a mailbox to receive their messages requires a level of ingenuity that borders on madness. The IceCube Observatory is that mailbox, a feat of engineering that turns a cubic kilometer of Antarctic ice into a giant detector. Suspended throughout this frozen volume are over 5,000 ultra-sensitive light sensors, arranged on long strings that descend into the deep ice. These sensors are not looking for the neutrinos themselves, but for the extremely rare occasion when a neutrino actually does interact with an atom in the ice. When a high-energy neutrino smashes into the nucleus of an atom, it can create a secondary charged particle that briefly travels faster than the speed of light in that ice. This generates a faint blue flash of light known as Cherenkov radiation, a luminous cone that spreads through the pristine ice like a sonic boom of light. The network of sensors precisely maps the direction and energy of this light, allowing physicists to trace the neutrino's path back to its origin in the distant cosmos. It is an exercise in cosmic patience, waiting for the universe to send a signal so faint that it requires a continent of ice to see it. For decades, scientists detected neutrinos, but their cosmic origins remained a mystery. The breakthrough came in September 2017, when IceCube detected a single, exceptionally high-energy neutrino. What made this event so revolutionary was that IceCube sent out a rapid alert to astronomers worldwide, who immediately swiveled every available telescope, from gamma-ray observatories to radio arrays, toward the direction in the sky it came from. There, in the constellation Orion, they found the source, a blazar known as TXS 0506 + 056, a galaxy 4.5 billion light-years away with a supermassive black hole at its core, spewing a jet of radiation and particles directly toward Earth. This was a watershed moment in science, the first time a single neutrino had been conclusively traced back to an astrophysical source, inaugurating the new field of multi-messenger astrophysics. This discovery provided the long-sought smoking gun for the origin of cosmic rays, a puzzle that has baffled physicists for over a century. Cosmic rays are high-energy protons and atomic nuclei that constantly bombard Earth, but because they are charged, their paths are bent and scrambled by magnetic fields throughout the galaxy, making it impossible to trace them back to their source. The production of these cosmic rays, however, is intrinsically linked to the production of neutrinos. Inside the relativistic jet of a blazar, protons are accelerated to nearly the speed of light. When these ultra-fast protons collide with other particles or photons within the jet, they create a shower of secondary particles, including neutral pions that decay into gamma rays and charged pions that decay into neutrinos. The detection of a high-energy neutrino from a blazar confirms for the first time that these monstrous engines are indeed powerful proton accelerators, factories for the cosmic rays that have permeated our galaxy. The ghost particle was the missing witness that finally tied the crime to the culprit. The implications of this are profound. Neutrinos allow us to see directly into the heart of these cosmic powerhouses, into regions so dense with radiation and matter that even light cannot escape. Gamma rays and X-rays can be absorbed or scattered by surrounding material, but a neutrino slips through effortlessly, carrying its information directly from the engine of the blazar, the turbulent accretion disk, and the base of the jet near the event horizon of the supermassive black hole itself. By combining the neutrino data with observations from light telescopes and gravitational wave detectors, we are no longer just looking at the universe, we are feeling its vibrations, tasting its particles, and listening to its whispers all at the same time. Each high-energy neutrino captured by IceCube is a direct telegram from the edge of a black hole, a piece of pure, unadulterated information about the most extreme physics in the cosmos, opening a new window through which to observe the universe's most violent and energetic transformations. But just as we look for cosmic messengers from distant galaxies, one of the most compelling astronomical mysteries might be hiding right here in our own cosmic backyard. This brings us to the 21st bizarre event, the tantalizing and controversial hunt for a hidden giant, the Planet 9 hypothesis. Imagine our solar system not as a completed map, but as a partially explored frontier where the gravitational whispers from the outer darkness suggest a colossal, unseen world is pulling the strings. This isn't about reclassifying Pluto, it's about the possibility that our sun has a true ninth planet, a frozen behemoth so far away that it has eluded our gaze for centuries, yet whose influence is written in the peculiar paths of smaller, icy objects. The entire case for this hidden world rests not on a direct sighting, but on the strange ballet of distant, icy bodies in the Kuiper Belt, the ring of frozen debris beyond Neptune. Astronomers studying these trans-Neptunian objects began to notice something deeply odd. A cluster of these small worlds, known as extreme trans-Neptunian objects, share a peculiar orbital characteristic. Their orbits are not randomly oriented. Instead, they appear to be grouped together, their points of closest approach to the Sun, their perihelia, clustered in the same general region of the sky. Even more strangely, their orbits are tilted in a similar way, all leaning over at roughly the same angle. For this to happen by random chance is astronomically improbable. It's as if you dropped a handful of marbles on a flat table and they all rolled to the same corner and tipped over in the same direction. This orbital clustering is the primary clue that has sent scientists on this modern-day planetary hunt, suggesting the gravity of a massive, distant object is herding these smaller bodies into these peculiar, aligned orbits. So, what kind of world could be causing this gravitational disturbance? The hypothetical Planet 9 is not a small, rocky body like Earth or Mars. Based on the mathematical models needed to explain the observed orbital anomalies, it is predicted to be a true giant, a super-Earth or a mini-Neptune with a mass roughly 5 to 10 times that of our own planet. This would make it the undisputed fifth giant planet of our solar system. Its orbit, however, would be unlike anything we're familiar with. It is thought to be tremendously elongated and tilted, taking it on a colossal journey around the Sun that lasts between 10,000 and 20,000 years. At its closest approach, it might come within 200 or 300 astronomical units from the Sun, but at its most distant, it could swing out to a staggering 600 to 1,200 astronomical units. To put that in perspective, Neptune is only 30 astronomical units away. This proposed planet would be living in the frozen, sunless hinterlands of our solar system, a realm where the Sun is just a particularly bright star in an otherwise black sky. The very existence of such a world raises a fascinating and fundamental question. How did it get there? Our standard models of solar system formation don't easily account for a large planet in such a distant, eccentric orbit. This has led to several compelling theories about its origin. One leading idea is that Planet 9 formed much closer to the Sun, in the same region as Jupiter and Saturn during the solar system's chaotic infancy. In a gravitational pinball game between the young giant planets, it could have been flung out into the distant reaches, its orbit stretched and tilted by a close encounter with Jupiter or Saturn. Instead of being ejected entirely, it was sent on this vast, lonely loop, forever bound to the Sun but forever distant. Another, more exotic possibility is that the Sun could have captured it. In the Sun's early life, when it was still nestled in its birth cluster alongside thousands of other stars, it's plausible that our Sun's gravity could have stolen a free-floating planetary mass object from a neighboring system, adopting this rogue world as its own. The search for this elusive giant is now one of astronomy's great treasure hunts, employing some of the most powerful telescopes on Earth. The challenge is immense. At such phenomenal distances, Planet 9 would reflect only a minuscule amount of sunlight, making it incredibly faint. Furthermore, astronomers don't know exactly where in its multi-thousand-year orbit it might be right now, so they have to scan vast swaths of the sky. Observatories like the Subaru Telescope in Hawaii and the Dark Energy Survey in Chile are leading the charge, using their wide-field cameras to take deep images of the sky, night after night, looking for a single, slow-moving point of light against the background of fixed stars. They are looking for that telltale shift, that slight motion over days or weeks that would betray the presence of a solar system object. It is a painstaking, needle-in-a-haystack endeavor, but one with a potentially monumental payoff. Yet the Planet 9 hypothesis is not without its skeptics. Some scientists propose that the observed orbital clustering could be a statistical illusion, an artifact of observational bias. Because these extreme Kuiper belt objects are so faint and difficult to find, our surveys have only covered certain parts of the sky. It's possible that we've simply found a cluster of objects in one area because that's the only area we've looked deeply enough to find them. Others have suggested that the collective gravity of many smaller, unseen Kuiper belt objects could, in theory, produce the same herding effect without the need for a single large planet. The debate is healthy and ongoing, driving the need for more data and more sophisticated surveys. Whether Planet 9 is ultimately found or falsified, this scientific quest has already reshaped our understanding of the solar system's dynamic outer limits, revealing a realm far more complex and potentially richer with unseen worlds than we ever previously imagined. It stands as a powerful testament to the fact that even in our own celestial neighborhood, profound discoveries may still be waiting in the dark, their presence felt long before they are seen. Now we confront a signal from the cosmos that is both bewilderingly brief and impossibly powerful. Imagine a flash of radio light, a burst of energy so intense that in the span of a single millisecond, the blink of an eye, it can release more energy than our sun emits over 80 years. These are fast radio bursts, or FRB, and they represent one of the most electrifying puzzles in modern astronomy. For years after their initial discovery in 2007, these events were solitary ghosts. A telescope would catch a one-off blast from a distant galaxy, a spike on a graph, and then nothing. They would vanish without a trace, leaving astronomers with a spectacular signal but no way to ever find its source again. They were cosmic drive-by shootings, fleeting and utterly enigmatic. The leading theories for these one-off bursts pointed to catastrophic, singular events, the final, dying scream of a star being shredded by a black hole, or the colossal collision of two ultra-dense neutron stars. These were events that, by their very nature, could only happen once, but then everything changed. In 2016, astronomers made a breakthrough observation that shattered the single-event paradigm. They found an FRB source, now known as FRB 121102, that did something extraordinary. It burst again, and then again. This wasn't a one-off catastrophe, it was a repeater. The discovery of repeating fast radio bursts was a monumental shift in the mystery. It immediately ruled out any model that involved the total destruction of the source. You cannot have a star collide with another star twice. This repeating nature was our first major clue, narrowing down the list of suspects to objects that are capable of producing such titanic energies repeatedly without destroying themselves in the process. Suddenly, the hunt was no longer just for a signal. It was for a persistent, dynamic engine capable of these staggering, intermittent eruptions. So, what kind of cosmic engine can fire off these millisecond salvos again and again? The prime suspect in the case of the repeaters is an object we encountered earlier, the magnetar. We already know these ultramagnetic neutron stars are capable of generating starquakes that release unimaginable energy. A particularly violent crustal shift on a magnetar, a snapping of its crystalline surface under immense magnetic strain, could theoretically generate a shockwave that accelerates particles to near light speed, producing a brilliant, coherent blast of radio waves. This model fits beautifully for the repeaters because a magnetar can experience multiple quakes over its lifetime. Its crust is under constant, immense stress from its evolving magnetic field, making it a perfect candidate for a repeater source, a cosmic pressure cooker that periodically blows off steam in the form of these brilliant radio flashes. In a stunning confirmation of this idea, in 2020, a magnetar within our own Milky Way galaxy, SGR 1935+2154, erupted with a radio burst that, while not as powerful as the extragalactic FRBs, shared many of their key characteristics. This provided the first direct link between a known object and an FRB-like event, strongly implicating magnetars as at least one source for these phenomena. However, the story is likely not that simple. The incredible diversity in the behavior of repeating FRBs suggests there might be multiple pathways to creating them. Some repeaters are remarkably quiet for long periods, then suddenly enter a frenzied phase of activity, spitting out dozens of bursts in a matter of hours. Others show a fascinating downward drifting pattern in their frequency. As you listen to the burst, it starts at a high pitch and rapidly slides down to a lower one, like a cosmic slide whistle. This complex structure implies a dynamic and intricate emission process happening within the source. Could all of this be explained by magnetar quakes alone? Perhaps, but some scientists speculate that for the most energetic and complex repeaters, the magnetar might need to be in a special environment, such as embedded within the dense, energetic nebula of debris left over from the supernova that created it. In this scenario, the radio burst from the starquake has to travel through this chaotic cloud, which could shape and sculpt the signal we eventually detect, creating the complex patterns and frequency drifts that make each repeater unique. Of course, whenever a mysterious, structured signal arrives from deep space, one hypothesis always captures the public imagination. Could it be alien technology? The precision and power of FRBs, especially the repeaters, inevitably lead some to wonder if we are detecting evidence of an advanced civilization. Perhaps these bursts are power beams for interstellar light sails, propelling vast spacecraft across the gulfs between stars. Or maybe they are a form of cosmic communication, a galactic internet we are only just beginning to eavesdrop on. While this is a thrilling notion, the scientific consensus heavily favors a natural origin. The sheer energy involved is astronomical, on a scale that seems to require the physics of extreme objects like neutron stars. Furthermore, the signals are spread across a wide band of radio frequencies, which is an inefficient way to send a targeted message. It's like trying to have a private conversation by screaming on every radio station at once. Most convincingly, the fact that we have now traced several FRBs, including repeaters, back to specific ordinary galaxies, and in one case to a magnetar in our own galaxy, strongly suggests they are a natural, if spectacular, part of the cosmic landscape. The true power of the repeating FRBs lies in their reusability as cosmic tools. A one-off burst is a tantalizing mystery, but a repeater is a persistent laboratory. Because astronomers know it will flash again, they can point the world's most powerful telescopes at its location for extended periods, gathering data across the entire electromagnetic spectrum, from radio waves to gamma rays, to see if the burst is accompanied by any other kind of emission. This multi-wavelength approach is crucial for pinning down the exact physics of the explosion. Even more profound is the potential of FRBs to act as cosmic weighing scales for the universe. As these radio waves travel across billions of light-years of intergalactic space, they pass through the diffuse, ionized gas that floats between galaxies. This gas leaves a specific fingerprint on the signal, causing different radio frequencies to arrive at slightly different times. By analyzing this dispersion, astronomers can essentially count the total number of free electrons the burst has encountered along its path. This provides a unique and direct way to measure the density and distribution of the ordinary matter, the atoms that make up stars, planets, and us, that is strung out across the vast cosmic web. These fleeting millisecond bursts are therefore becoming one of our most promising tools for mapping the invisible architecture of the universe itself, turning a profound mystery into a powerful new instrument for discovery. Yet for all the brilliant flashes and fleeting signals, the most majestic structure in the cosmos is also the most difficult to see. It isn't a star, a galaxy, or a nebula, but the very skeleton upon which the universe is built. Our 23rd bizarre event is the cosmic web, a sprawling spider web-like architecture of dark matter and primordial gas that stretches across billions of light years, forming the fundamental scaffolding for all of creation. For decades, this was purely a theoretical prediction. Supercomputer simulations told us that after the Big Bang, the slight irregularities in the infant universe were amplified by gravity. Dark matter, that invisible and mysterious substance, began to collapse first, forming an immense network of dense knots connected by long, winding filaments, with vast, empty voids stretching between them. Ordinary matter, the gas that would become stars and galaxies, was then simply swept along, flowing into this pre-existing dark matter blueprint. Galaxies didn't form randomly. They were born at the intersections of these filaments and strung along them like glittering pearls on an invisible string. Mapping this phantom structure directly has been one of astronomy's grandest challenges, because the filaments themselves are made predominantly of dark matter and incredibly diffuse million-degree gas that emits almost no light. But scientists have developed ingenious ways to illuminate the darkness. One powerful method uses the light from distant quasars, the intensely bright cores of active galaxies. As this brilliant light travels across the universe on its way to our telescopes, it passes through the faint, warm gas within the cosmic web filaments. Atoms in this gas, like hydrogen and helium, absorbs specific wavelengths of the quasar's light, creating a unique barcode of dark lines in the quasar's spectrum. By studying thousands of quasars, astronomers can piece together a tomographic map, much like a medical CT scan, revealing the intricate, absorptive tendrils of the web that would otherwise remain completely hidden from our view. Another breathtaking technique involves a phenomenon known as the Sunyaev-Zeldovich effect. The sparse but incredibly hot gas trapped in the web filaments is filled with high-energy electrons. When the ancient light from the cosmic microwave background passes through this searing plasma, these electrons give the photons a tiny energy boost. By using incredibly sensitive radio telescopes to scan the sky, scientists can detect these subtle distortions in the CMB, pinpointing the locations where the background radiation has been slightly heated. This allows them to create a map of the web's gaseous component, tracing the colossal filaments by the faint shadow they cast on the oldest light in the universe. It is a direct glimpse of the universe's underlying architecture, a confirmation that the grand design predicted by our theories is woven into the very fabric of reality. This cosmic framework is not a static sculpture. It is a dynamic and living system that governs the life and death of galaxies. Think of the filaments as cosmic superhighways, channeling vast rivers of cold, fresh gas from the voids toward the hungry galaxies clustered at the intersections. This continuous flow is the primary fuel for star formation. A galaxy positioned at a major nexus of the web, like a city at the confluence of great rivers, will receive a constant supply of gas, allowing it to build new stars for billions of years and grow into a brilliant, massive elliptical galaxy. In contrast, a galaxy isolated in a quieter part of the web, or worse, stranded in a void, will see its gas supply slowly cut off. It becomes a galactic island, its star-forming fuel depleted, destined to age into a red and dead collection of old stars. The cosmic web is therefore the ultimate puppet master, pulling the strings of galactic evolution and determining their ultimate fate through the simple, relentless flow of gravity. The sheer scale of this structure is almost impossible to comprehend. In 2014, astronomers announced the discovery of one of the largest known structures in the universe, fittingly named the Boss Great Wall, a filament complex spanning more than 1 billion light-years. To put that in perspective, if you could travel at the speed of light, it would take you over 1,000 times the age of our solar system just to journey from one end of this single filament to the other. These are not mere features, they are the continents and mountain ranges of the cosmos on a scale that dwarfs anything we can conceive. Their existence and conformation stand as a triumphant validation of our modern cosmological models, a stunning reminder that the universe is not a random scattering of lights, but a highly organized, interconnected, and breathtakingly beautiful tapestry whose invisible threads hold the entire visible cosmos together. But if the cosmic web represents the universe's grandest architecture, our next phenomenon brings us back to a far more intimate and far more destructive celestial dance. We now arrive at the 24th bizarre event, a class of objects with a name as chilling as their behavior, the Black Widow pulsars. These are not your average, steadily ticking neutron stars. They are the ultimate cosmic predators, spinning at incredible speeds and blasting their much smaller stellar companions with such intense radiation and particle winds that they are systematically boiling them away into nothingness. It's a case of cosmic cannibalism so efficient and ruthless that it seems to have been engineered by nature itself to push the laws of physics to their absolute breaking point. At the heart of every Black Widow system is a millisecond pulsar, a neutron star that has been spun up to rotational speeds of hundreds of times per second. This incredible spin is the result of a prior and ultimately fatal act of vampirism. The pulsar began its life in a binary system with a normal, sun-like star. As that star aged and expanded, the dense neutron star's gravity began to siphon material from its companion. This stolen gas didn't just fall onto the pulsar, it spiraled in, forming a whirling disk of superheated matter. As this material crashed onto the pulsar's surface, it transferred an immense amount of angular momentum, acting like a cosmic whip that spun the pulsar faster and faster until it reached its millisecond period frenzy. This process, called recycling, essentially uses the lifeblood of the companion star as fuel to create one of the most precise timekeepers in the universe. But the story doesn't end there. This is merely the prelude to the main act of destruction. Now reborn as a hyper-spinning dynamo, the pulsar becomes a truly monstrous partner. Its rapid rotation powers an unimaginably strong magnetic field, which in turn generates a relentless gale of high-energy particles and radiation, a stellar wind of such ferocity that it makes the solar wind from our sun look like a gentle breeze. This wind slams directly into the nearby companion star, which is now a small, stripped-down remnant, often with a mass less than that of Jupiter. The effect is not a gentle heating, it is a brutal, continuous ablation. The pulsar's wind deposits so much energy into the companion's atmosphere that it literally blows the star's outer layers away, vaporizing it into a cloud of superheated plasma that slowly disperses into space. Imagine holding a blowtorch to an ice cube, not to melt it, but to instantly turn it into steam. That is the level of violence occurring in these systems, a process that is, right now, systematically erasing a star from the universe. This ongoing evaporation creates a haunting and telltale signature that astronomers can detect from Earth. The systems are often discovered because of the incredibly regular pulses of gamma rays or radio waves from the spinning pulsar. However, these pulses are periodically eclipsed. The cloud of vaporized material being boiled off the companion star forms a vast, diffuse shroud that occasionally passes between us and the pulsar, blocking its signal for a short time. By studying the timing and depth of these eclipses, scientists can measure the rate of mass loss from the doomed companion, watching in real time as a star is slowly disassembled. The ultimate fate of the companion is complete annihilation. The pulsar will continue to feed on it and blast it until there is nothing left but a wisp of ionized gas, leaving behind a solitary, rapidly spinning millisecond pulsar as the only tombstone for its devoured partner. Yet, the sheer extremity of Black Widow systems makes them far more than just gruesome cosmic curiosities. They have become some of the most valuable natural laboratories in the universe for testing one of the cornerstones of modern physics, Einstein's theory of general relativity. The key is their exquisite timing. A millisecond pulsar is a clock of phenomenal stability, its radio pulses arriving on Earth with a predictability that rivals our most advanced atomic clocks. However, in the intense gravitational environment of a tight binary system, this precise ticking is subjected to subtle distortions that provide a perfect testing ground for relativity. The first and most profound test comes from the emission of gravitational waves. As the pulsar and its companion orbit each other, they lose orbital energy by rippling spacetime itself, causing their orbits to very slowly decay. By meticulously tracking the arrival times of the pulsar's pulses over years, astronomers can measure this orbital decay with breathtaking precision. The observed rate of decay has been found to match the predictions of general relativity for gravitational wave emission to within a fraction of a percent, providing some of the most stringent and convincing evidence for the existence of gravitational waves long before they were directly detected by LIGO. But the tests don't stop there. In some of these systems, the effects are so pronounced they allow for checks of even more subtle relativistic effects. One such phenomenon is the Shapiro time delay, which occurs when the radio pulses from the pulsar travel through the curved spacetime around its companion star. As the pulses pass close to the companion, their path is lengthened by the warping of space, causing a tiny but measurable delay in their arrival time on Earth. By observing this delay, scientists can essentially weigh the companion star with incredible accuracy. Another effect is geodetic precession, where the spin axis of the pulsar itself slowly wobbles like a top due to the dragging of inertial frames as it moves through the curved spacetime of its orbit. Each of these observed effects is a victory for Einstein's theory, demonstrating its predictive power in gravitational fields far more extreme than anything found in our solar system. The continued survival of general relativity under such intense scrutiny in these brutal systems is a testament to its profound description of the very nature of space, time, and gravity. And with that, we arrive at our 25th and final bizarre event, a mystery that is perhaps the most profound of all because it surrounds us with a deep and unsettling quiet. After our breathtaking tour of a universe filled with stellar vampires, diamond worlds, and colliding galaxies, we are left facing a single haunting question. Given the sheer immensity of the cosmos, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, and the growing realization that most of those stars likely host their own families of planets, many of them in the so-called Goldilocks zone where conditions could be just right for life. The numbers alone suggest that the universe should be absolutely teeming. Life, the stage is unimaginably vast, the raw ingredients for biology are everywhere, and the play has been running for over 13 billion years. And yet, when we train our most sensitive instruments on the heavens, listening for any whisper of a signal, any signature of technology, or any sign of cosmic engineering, we are met with nothing. A profound and unnerving silence. This is the Fermi paradox, a contradiction of cosmic scale that asks one of humanity's oldest and most fundamental questions: where is everybody? The very origin of this paradox lies in a casual lunchtime conversation. The story goes that in the summer of 1950, physicist Enrico Fermi was discussing the possibility of flying saucers with colleagues at Los Alamos National Laboratory. As they chatted about a recent spate of UFO reports and a cartoon about aliens stealing garbage cans, Fermi, famous for his back-of-the-envelope calculations, suddenly looked up and asked, "But where is everybody?" His point was razor-sharp. If intelligent, spacefaring civilizations were common, even if they expanded at a modest fraction of the speed of light, the mathematics are inescapable. They could have colonized our entire Milky Way galaxy within just a few tens of millions of years, a mere eye blink in the galaxy's 13 billion-year history. The fact that we see no evidence of such a galactic civilization, no vast construction projects, no interstellar traffic, and no visitors on our doorstep, strongly implies that something is terribly wrong with our optimistic assumptions. The universe presents us with a colossal arena seemingly set for a grand cosmic opera, but when the curtain rises, the theater appears to be empty. This silence has compelled scientists to propose a range of resolutions, some comforting, others deeply sobering. The explanations generally fall into two broad camps: those that suggest intelligent life is exceedingly rare or short-lived, and those that propose it is common, but we are simply not looking in the right way or at the right time. Let's explore some of the most compelling ideas. One of the most popular is what's known as the rare Earth hypothesis. This line of reasoning argues that while simple microbial life might be common, the emergence of complex, multicellular, and ultimately intelligent life requires such a precise and unlikely chain of planetary and astronomical circumstances that it may have happened only once in our galaxy, or perhaps in the entire observable universe. It points to factors far beyond just being in a habitable zone. We needed a large moon to stabilize our planet's axial tilt, preventing wild climate swings. We needed a Jupiter-like giant planet in just the right orbit to act as a gravitational shield, deflecting a barrage of life-extinguishing comets. We needed the right kind of star, one that is stable for billions of years and doesn't produce lethal flares. We needed plate tectonics to recycle nutrients and regulate our climate. When you add up all these just right conditions, the number of potential Earth twins in the galaxy could plummet from millions to just a handful or even one. Then there is the chilling possibility known as the Great Filter. This theory suggests that the evolution from non-life to a spacefaring, galaxy-colonizing civilization involves passing through a series of critical, difficult steps. The Great Filter is a barrier, a developmental wall that is so hard to get past that it effectively stops nearly all life in its tracks. The terrifying question is, where is this filter located in our own timeline? If it lies in our past, for instance, in the improbable jump from non-living chemistry to the first self-replicating molecule, or in the transition from simple prokaryotic cells to complex eukaryotic cells, then we are an incredible 1 in a trillion fluke, and the silence is explained because we are truly alone. The more unsettling alternative is that the Great Filter lies in our future. Perhaps the development of advanced technology inevitably leads to a self-destruction mechanism, nuclear annihilation, a runaway engineered pandemic, or an out-of-control artificial intelligence that every civilization ultimately fails to navigate. In this grim scenario, the silence is a cosmic graveyard, and the stars we see at night are not beacons of hope, but the unmarked tombstones of civilizations that rose, flourished, and then vanished, leaving no trace behind. On the more optimistic side of the spectrum, there are explanations that don't require such a lonely or tragic fate. Perhaps we are simply not listening correctly. Our current search for extraterrestrial intelligence, or SETI, is like trying to find a specific conversation in a crowded city by listening through a single, narrow keyhole. We primarily search for deliberate radio or laser beacon transmissions, but a truly advanced civilization might use communication technologies we can't even conceive of, such as neutrino messaging or quantum entanglement, which would be completely invisible to our current detectors. Or maybe they are out there and they are signaling, but their transmissions are so compressed or so advanced that we simply register them as cosmic background noise. Another fascinating idea is the zoo hypothesis, which posits that advanced galactic civilizations are fully aware of our existence, but have deliberately placed us in a kind of cosmic quarantine or wildlife preserve. They are observing us from a distance, following a strict policy of non-interference to allow our civilization to develop naturally, without outside influence, until we reach a certain level of technological or ethical maturity. In this view, the silence is not an absence, but a respectful, patient observation. There is also the humbling possibility of cosmic timescales. The universe is 13.8 billion years old, and our technological civilization is less than a century old. What are the odds that another civilization is broadcasting in a way we can detect at the exact same century we are listening? Intelligent civilizations could be like flashes of fireflies in a vast, dark meadow, brief, brilliant, and almost never synchronized. The galaxy could be dotted with the ruins of ancient empires that fell 100 million years ago, or it could be waiting for the first sparks of intelligence to ignite millions of years in the future. We might be early to the party, or we might have arrived long after the music stopped. This synchronization problem means that even in a galaxy teeming with intelligence, every civilization could spend its entire history in a state of profound isolation, separated by chasms of time so immense that communication becomes virtually impossible. And so, our journey through 25 bizarre cosmic events brings us full circle back to ourselves. The Great Silence is not just a puzzle about them, it is a mirror held up to us. It forces us to confront our own future and our own responsibility. Are we a miraculous accident, a lone spark of consciousness in an endless, sleeping void? Or are we one voice in a cosmic chorus, on the cusp of finally learning how to listen and join the conversation? The answer to the Fermi paradox will likely define humanity's ultimate place in the universe. For now, the silence persists, a blank canvas onto which we project our deepest hopes and our most profound fears. It is a mystery that remains unsolved, a question mark hanging over the cosmos, challenging us to continue looking up, listening carefully, and striving to ensure that our own faint signal does not one day fall silent, becoming just another unanswered whisper in the eternal cosmic dark. And so our voyage through the cosmos concludes not at a final destination, but at the edge of a vast and ever-deepening mystery. We have ventured from stellar vampires siphoning the life from their neighbors to ghostly planets wandering the interstellar void, from the silent, chilling cold of the Boomerang Nebula to the rhythmic heartbeat of a feeding black hole. We have witnessed the cosmic geometry of Hoag's object and felt the unsettling pull of the Great Attractor, all while grappling with the profound silence that answers our calls into the dark. This journey through 25 of the universe's most bizarre events reveals a critical truth. The cosmos is not a static museum display, a collection of distant, timeless points of light. It is a living, breathing, and violently dynamic arena, a grand stage where the laws of physics are stretched, tested, and sometimes seemingly rewritten in real time. The tranquil night sky is a beautiful illusion, a curtain veiling a continuous, chaotic, and breathtakingly beautiful drama. These phenomena are not relics of a distant past sealed away in some cosmic history book. They are happening right now. At this very moment, a runaway star is plowing through a cloud of interstellar gas, forging a brilliant bow shock. Deep within a galactic core, a supermassive black hole is ripping a star apart. In the frozen depths of space, a rogue planet drifts in perpetual night, while in the heart of a dying star, complex organic molecules are being forged and cast out into the void. Every single one of these events is an active process, a thread in the ongoing tapestry of cosmic evolution. They are actively shaping the fate of galaxies, seeding space with the elements for new worlds and potential life, and dictating the ultimate destiny of the universe itself. We are not separate observers of this spectacle. We are embedded within it, our very existence made possible by the long-ago explosions of stars and the relentless, creative, and often destructive forces we have explored. This journey underscores an even more profound point. Our understanding is perpetually incomplete. The Hubble tension, the dark flow, and the enigma of odd radio circles are not signs of failure, but blazing beacons guiding us toward the next great discovery. They are the frontiers of our knowledge, the places where our current models fray and new physics awaits. Each mystery solved, like the refined age of the Methuselah star or the dusty explanation for Tabby's star's dimming, doesn't close a book. It opens a new volume filled with more nuanced and fascinating questions. The universe is not getting simpler as we learn more. It is revealing layers of complexity we never dreamed possible, inviting us to remain forever curious, forever humble, and forever in awe. So, the next time you find yourself beneath a clear, dark sky, I invite you to do more than just admire the serene beauty. Look up and truly see. See the diamond worlds glittering in infernos, the cannibal galaxies slowly reshaping themselves, and the ghostly particles silently passing through your body from events billions of light years away. Let that view fill you with a renewed sense of wonder for the incredible, bizarre, and dynamic cosmos we are so privileged to call home. The greatest show is not on any screen. It's happening all around us, an epic story of creation and destruction unfolding on a scale both humbling and exhilarating. We would love to continue this conversation with you. Share your thoughts in the comments below. Which of these 25 bizarre events captured your imagination the most? Was it the destructive fury of Eta Carinii, the perfect geometry of Hoag's object, or the profound mystery of the Great Silence? Your perspective is part of this ongoing human journey to understand our place in this strange and magnificent universe.